Okay, so what we were discussing in yesterday's class is really very, very important. Very important. So please learn this concept in a very detail, understand it very deeply about homogeneous, non-homogeneous, and the conditions of consistent system of equations where there will be no solution, where there will be unique solution, and where there will be just infinite solutions. So let's go to the next example. The value of lambda. If the equation, one equation with two variables, another equation with two variables, and another equation with two variables are consistent. So we have the system of three equations and two variables. Okay, and this system is given as consistent. Consistent means that there will be certain solution for it. So let's write these given equations in a certain manner. So the coefficient of z is 0 everywhere, 0, z. Bringing the constant on the right hand side, 1 plus lambda into x plus 2 plus lambda into y plus 0 into z is equals to 8. When it is brought to the right hand side, let's talk about the third equation. X minus 1 plus lambda into y plus 0 into z, because there are no z's. There are not z. So we are writing at 0 z is equals to minus of 2 minus lambda. Okay, great. We have written all of the three given equations. Okay, so now if we write the delta here, we write the determinant of A here that we have discussed earlier, D. So the coefficient of x, y, and z, yes. So the coefficient of x is 1, 1 plus lambda here, and 1 here. 1 here, 2 plus lambda here, minus of 1, minus of lambda here. Here, 0, 0, 0. So the determinant is given as 0. Now we know that if d is 0, and basically the coefficient d is 0, and d1, d2, d3 are also going to become 0, that is for sure. Right? Why? Because the system of equation is given as is homogeneous in nature. What we were discussing earlier. Yeah, here. So the condition was if d1, d2, d3 are 0, then the system is called to be then the system is called to be homogeneous. Otherwise, this is other condition. Okay. So let's not confuse it by reading it. That if determinant of 1, 2, and 3 metric determinant has become 0, then the system is homogeneous. And when the system was homogeneous, then system was having solution only when there will be infinite value of x, y, and z, and the system will be called consistent only when d is 0, which is 0 in our case, right? Here we can see d is 0 in our case, but it is given as consistent. So it is for sure that why? Because d1 here, try to find out. D1 is basically the replacement of first column with the values 3, 8, and 2 minus 2 minus lambda remaining. So here there will be same columns. First and second and third column will be the same. Okay. Laptop stuck. Okay, so the third and second and third column are the same. So let's write them here also. They are the same. Okay. This is unnecessary. So this is how D1 looks like. Its value will be 0 for sure because the whole column is becoming as 0. And the D1 will be 3, 8, minus 2, minus lambda. So similarly, we can write d1, d2, d3. All are 0. That's why the system of equation is homogeneous in nature. But we have got to find out the value of lambda. We'll be only able to do so when this third column gets replaced. So we know d3, this third column will get replaced by 3, 8, minus 2, minus lambda, and the remaining columns will be the same. Okay, so let's copy paste it to save our time. The first and second column going to remain the same because it's d3. Okay, this is how d3 is going to look. Now we know the system of equation given is homogeneous because the variable, the coefficients of z in all the three equations are 0. That's why we are concluding so. Okay, so if this is going to become 0, so let's solve this particular determinant. Okay, now let's bring this particular determinant on the next page for solving. They're having more space. Now, we have discussed earlier, we can assume values of lambda, but there are so many options with so many values. So instead of assuming and checking 8 times 8 lambda, 8 values of lambda, we can similarly simply just solve the determinant, given determinant. Now we know the basic objective and the basic trick for solving an determinant is to make the maximum number of 0 in any row or any column. So we can spot by looking at on it that we'll be able to minimize and make we can make this element 0, right? We can also make this element 0. How we can do so? By subtracting 1 from this particular element, we'll be able to make it 0. So let's apply the operation of on column number second, that we are subtracting column number first from column number second. So after doing this operation, there will be only changes in column number second. So the remaining will remain the same. Now the second column will 1 minus 1, 0, 2 plus lambda minus 1 plus lambda. So lambda cancels, 2 minus 1 becomes 1. Minus 1 lambda minus 1. That becomes minus 2 minus lambda. Great. This has become 0. Let's try to make this 0. Okay. So this will become 0 when there is an operation of column number 3. And when we'll subtract column number 3 from 3 times multiple of column number 1. Okay. So let's do that. Only there will be changes in column number 3. Writing column number 1 and 2 as it is. 3 minus 3 minus of 1 into 3, that becomes 3 minus 3, 0. 8 minus 3, 5. Minus of 3 lambda. Now, minus 2 minus lambda, minus of 3. This is minus 5 into minus lambda. So this has to become 0. This has to be 0. Now we will solve using the first row because there are 2 zeros in it. So using solving and expanding the determinant using the first row. Okay. So the first element into its cofactor. Okay. 1 into minus 5 into minus lambda. Minus of 5 minus 3 lambda into minus of 2 lambda. So minus of 5 minus 3 lambda into minus of 2 minus of lambda. And plus means 0 into something becomes 0. 0 into something becomes 0. Doesn't matter. And that is if that is 0, so let's not write then even save space. And that was given as equals to 0. So 1 getting multiplied to anything, it's insignificant. The same expression will be left out. Okay, so minus 5 minus lambda. Now, this minus will cancel both of these minus after getting multiplied. Is that correct? So let's now multiply these two terms first. So 5 into 2 plus 10. 5 into lambda plus 5 lambda. Minus 3 lambda into 2 minus 6 lambda minus 3 lambda into lambda minus of 3 lambda square. Now the equation is in quadratic. There will be two roots for the value of lambda. So let's now solve it without doing any calculation mistake. So let's now bring the 3 lambda square on the right hand side. So on the left hand side, everything will be taken to the right hand side. So minus 3 lambda square will make it plus 3 lambda square. Minus 6 lambda plus 5 lambda makes it minus of lambda, right? Minus minus lambda, minus 2 lambda. When minus 2 lambda is passed over to the right hand side, then it becomes positive, plus 2 lambda. Plus 10 minus 5 plus 5. Plus 5 goes to the right hand side, becomes minus of 5. We have already written 3 lambda square on the right hand side. So we have written and we have covered all of the terms. Now let's find out two factors whose product is minus 5 by 3. Okay. And product is minus 2 by 3. So the root seems complex. So let's use the Sridharacharya formula. X is equals to minus of b plus minus square root of determinant. Sorry, discriminant. This is discriminant, not determinant. This is discriminant. Upon divided by 2a. So, okay, you have looked at the formula once. Now let's save the space. X is minus of b minus 2 plus minus b square, that is 4 minus 2, 4 into AC, b square minus 4 AC. So A is 3, C is minus of 5. Minus minus cancels each other, divided by 2, 2 into 3. Now let's divide. Okay, now let's solve it first. 4 into 3 becomes 12. 12 into 5 becomes 60. 60 plus 4 becomes 64. So square root of 64 is what? 8. Minus 2 plus minus 8 divided by 2 into 3. Now let's divide by 2 for like with the both of the term. 2 cancels 2 with minus of 1. 2 cancels 8 with plus minus 4. So this has become minus 1 plus minus 4 divided by 3. If plus is considered, minus 1 plus 4, 3 by 3, which makes it 1. Sorry, we are not solving for x. We are solving for lambda. So one value of lambda is 1. Minus 1 minus 4 becomes minus 5 divided by 3. So these are the two values of lambda. Yes, it is matching with the option number C, which is the correct answer. So this is what we have done. We were asked with the lambda value. We have observed the equation and we have concluded that the given set of equation is homogeneous. That's why every d1, d2, d3 should be becoming 0 when it is given that the solution is consistent. Okay, so conveniently we have find it out d3 because there was lambda, we were able to solve this determinant. Other determinants will becoming directly 0 with the effect of a single column. This column got replaced in d3. That's why we were able to solve and find out the value of lambda using d3 and expanding it and doing some operations. Is that clear, everyone?
Yes, sir.
Great. Let's move ahead then. Yes, it's our correct answer. So these are some properties of determinants. Let's cover them one by one. Thereafter, we'll conclude our class. The first property says that the determinant of B matrix is equals to K into determinant of A when B is obtained from A, when A got multiplied with the one row of A got multiplied with K, then the determinant of B becomes K multiple of determinant of A. Basically, what they are trying to say is determinant of, let's say there's a matrix. Okay, there's a determinant A, B, C, D, E, F, G, H, I. If I multiply, let's say this is equals to X. If I multiply 2 with the first row, 2A, 2B, 2C, and others remains the same. then the determinant also become twice. If I multiply 2 with second row also, then once again it's got multiplied with 2. If I multiply 3 with third row, then again it get multiplied with 3. So this is the logic behind. Is that clear, everyone? Clear? We have also discussed about the same property earlier. Any doubts?
No, sir.
Okay, let's now discuss the next property. Determinant. Okay, it is the same. It is the same that we have just discussed. That if you are going to multiply a k scalar with all the metrics, okay, then k will be taken common from each and every row. So the determinant will make it as number of rows that were there. So we know the number of rows and number of columns are equal. So k into n raised to power a, which was the original matrix. Okay. Any doubts, anyone?
No, sir.
The next point says, if A, B, C are square matrices, the same order that of that ith column or row of A is the sum of, basically this is that if determinant A is can be expressed as the sum of these two matrices, then their particular determinant are also going to follow this particular relation. Okay. If A matrix can be expressed as the sum of two matrices, then the determinant of the matrix B and the determinant of matrix C, the sum of their determinant will equal to the parent matrix determinant. This is the point. Coming to the next property, if A is a non-singular matrix, non-singular means if A's determinant is non-zero, then its inverse will definitely exist. Okay, it is an invertible matrix. If there is any matrix whose inverse exists, then we may call it invertible matrix. So the determinant of inverse matrix is simply equals to the inverse of the determinant of the matrix, as simple as that. Coming to the next property, determinant of a skew symmetric matrix. What is a skew symmetric matrix? Let me just write a pattern whose diagonal elements are zero. Basically, the definition is this: when any matrix transpose equals to the negative sign of the determinant, then A is a skew symmetric matrix. Okay, so this particular matrix will look somewhat like this. Okay, there will be opposite signs with respect to the diagonal, and the principal diagonal will be having zero elements. So this is how a typical skew symmetric matrix looks like. Okay, let's now discuss about the determinant of a skew symmetric. If there is a skew symmetric of order, if there is any A skew symmetric matrix of order even, then its determinant will equal to some perfect square, some number. Okay, so it will be like, it can be basically, my point is this: the determinant of the matrix can be written as the perfect square of some other number. Okay, if the order is even can be 2 by 2, 4 by 4, 6 by 6. And if the order of the matrix is odd, 3 by 3, 1 by 1, 5 by 5, then the matrix is going to become its determinant is going to fourth floor become 0. So every skew symmetric matrix, this is the skew symmetric matrix. every skew symmetric matrix of order odd, its determinant is 0. So every skew symmetric matrix of 3 by 3 order, its determinant will be 0 for sure when A is a skew symmetric matrix. Is that property clear, everyone? Now let's discuss that if A matrix is there and it is expanded in as B plus C, then it is not necessary that the determinant will be equal. Earlier also we have talked about the same property, but there was a difference. There is a difference between these two, that the columns, respective columns were getting expanded, not the entire matrix. Okay, respective columns are getting expanded. That is only when we can express the determinant as the sum of other two. So it's not a necessary situation. It may happen, but it's not necessary when any matrix is written in the addition of in the expression of addition of two matrices. Okay. Earlier it was happening because there were only one row or one column that was getting expanded. See, it is mentioned ith column is of A is the sum of ith columns of rows or like of ith columns of B and C. It's only specifically talking about ith row. It is a difference. Is that point clear, everyone? If there is any doubt, please do ask me. No doubts?
No, sir.
Okay, let's now talk about the next property. The determinant of a diagonal matrix. Diagonal matrix means there will be only elements available in the diagonal position. Otherwise, all the elements will be 0. So the determinant of any diagonal element, diagonal matrix, will be the product of the diagonals. Simple. Determinant of a triangle matrix is also the product of its diagonal elements. Diagonal elements that only these elements are there. The other remaining elements are 0. Let's now talk about the next property. Determinant of an unit matrix is 1. As simple as that. Determinant of a null matrix is 0 for sure. Symmetric determinant. Okay, so now this is the basic. This is a symmetric matrix whose determinant is equal to its matrix. So its formula is given to you. You may learn it, and I don't advise you to learn. It's simple. You can just solve it, right? But still, if you want to learn it, you can. Now, we know the skew symmetric matrix determinant is 0 when its owner is odd. Now, these are the things which you can learn. Okay? These are direct results. After operating, they were able to find out these identities. These first 4 are really important. Now, this is property. Now, what this particular property is saying, that if there is a determinant having functions, now if there is any determinant having function in one of its row, and if there is something some operation going on, now this particular operation is called sigma operator, and its function is to like, if this is written that sigma operator on function r is to 1, r is equating from 1 going to n. It means that f of 1 plus f of 2 until f of n. It's its meaning. This is called pi operator. So let's say if it is operating on this function, so it means f of 1 getting multiplied to f of 2, getting multiplied again and again till n. So this is what the pi operator means. Is that clear, everyone?
Yes, sir.
So simply it is given that if there is any determinant having functions and if there are operators acting, so you may directly apply the operator on the respective row or code. Okay, so this is about the chapter determinants. In this chapter, you will have to use your clever techniques. You have to be lazy. You have to sometimes put value, or you have to operate wisely. And the objective for applying operations will be to make maximum number of zeros and ones in the row and solve and expand that determinant using that row only. Homework is to solve previous year questions. Is there any other doubt regarding determinants chapter?
No, sir.
Doubts? No doubts. Okay, so let's conclude the class now.